Hello friends, today we are going to see the next process in ideal gases, that is the constant temperature process. It is also called as the isothermal process. So today we will discuss about the different analysis parameters on the isothermal process, and we will solve the simple numerical on isothermal process or the constant temperature process. So in the constant temperature process, which parameter we are keeping constant? Just like the previous two processes, we have seen in the first process that was volume was constant in the isochoric process. In the second process, the pressure was constant, that was the isobaric process. And in case of the isothermal process, it is a constant temperature process. So temperature is assumed to be remaining constant during the process. Now, on the slide we can see the definition of the process. The process in which temperature of the gas remains constant during expansion and compression is called as the isothermal process. Consider the arrangement of frictionless piston cylinder arrangement as shown in the figure for this process. Now, whenever we are dealing with the ideal processes, the conditions in which ideal processes are carried out, those conditions are the ideal conditions. So in this case we are considering the piston cylinder mechanism, but what is the requirement for this mechanism? That is, it should be the frictionless piston cylinder arrangement. So friction should be zero, so that the internal heat will not be generated during the process. Therefore this process we are considering that the temperature is remaining constant during the process. So we can see this piston and cylinder arrangement. If you consider a 1 kg of gas is taken for the analysis, and we are adding the heat initially to this particular process. Now whenever we are adding the heat, there will be the expansion of the gas molecules. The molecules will go away from each other, and because of that we see that the specific volume of the gas will increase. As the volume of the gas is going to increase, we see that the volume of the total system is also going to increase. Therefore, as this piston moves outward because of the expansion of the gas, we say that there is a work output we are getting from this particular expansion process whenever the heat is added. Now we are assuming that the temperature is remaining constant. Now when the temperature is going to remain constant? When system and surrounding, they are always maintained in a thermal equilibrium condition. Now to maintain the system and surrounding in the thermal equilibrium condition, whatever process we are carrying out, that should be very slow process, so that there should be a time for the heat transfer to take place. So whenever we are adding the heat here, we see that expansion has taken place, but we know that during the addition of the heat, the temperature, pressure, volume, all the three parameters are going to increase. But if this process is very slow, we will get time for the heat energy to go out, so that the temperature will be reduced during the initial state or during the changes of the state. Therefore this process should be carried out very slowly, so that we will have the heat transfer between the system and surrounding, and they both will come into the thermal equilibrium condition at each stage. Therefore the temperature of system and surrounding will be always equal. So it is not practically possible, because we cannot carry out this process very slowly because of the expansion of the molecules. The sliding effect of the piston will be rapid. So this is the ideal concept. So we are assuming that temperature is going to remain constant, and system and surrounding are always remaining in the thermal equilibrium condition during the process. So we are representing this particular expansion process on PV diagram and TS diagram as shown in the figure. So initial state point, we have to measure all the parameters, all the properties, just like pressure, temperature, initial volume before the heat addition, and then we can plot this point number 1 on the PV diagram. Now when the process is carried out, when the heat is added, we see that this process curve is moving along the constant temperature line. Here the volume is increasing, but pressure is decreasing because of the increment in the volume. But this is the process which is moving along the constant temperature line. So temperature T1 is equal to temperature T2. So this is the final condition, final state point T2 of the isothermal process. Now here we can see that whatever the heat is added, heat is the input energy for this particular expansion process, and work is the output energy from this particular process. So we are calling this process as the expansion process. Now on the expansion process, we are representing that on the TS diagram, that is the temperature entropy diagram. We can locate again the initial state point before addition of the heat and final state point when the addition of the heat is over. So we are getting a horizontal line as a process curve in which the temperature T1 is equal to temperature T2. But as we are adding the heat, we see that the entropy of the gas is increasing from S1 to S2. Similarly, internal energy will also increase from U1 to U2, and enthalpy will also increase from H1 to H2, because all these parameters, they are the function of heat addition and heat rejection. Therefore, in the expansion process, we can see here from the state point 1 to 2 on the temperature entropy diagram, we see that the entropy is increasing from S1 to S2 during the expansion of the gas. So this is about the isothermal expansion process. Now in the reverse direction, we can carry out the isothermal compression process. In isothermal compression process, we are not adding the heat here. We are doing the reversal of the isothermal expansion, in which what we are doing, we are providing the work energy to the system. So work input we are giving to the piston rod, and we are carrying out the compression. So we are calling it as a isothermal compression. But to achieve the thermal equilibrium condition, to achieve the temperature, that is the constant temperature process, we have to carry this process very slowly. Therefore, the temperature is remaining constant always throughout the isothermal compression process. So when we are compressing the gas by providing the work energy, we see that due to the compression of the gas, the volume is going to decrease and pressure is going to increase. So as the pressure increases, the temperature is also going to increase. Internal energy is also going to increase. Enthalpy is also going to increase. But as the temperature is remaining, we have to keep the temperature constant. We are moving this particular piston very slowly, so that thermal equilibrium can be always achieved. Therefore, when we are moving this particular piston, we see that volume is decreasing, pressure is increasing at constant temperature. So we can locate this particular process on PV diagram. So initial state point will be this point will be the initial state point, and along the constant temperature line, we are going towards the state point 2 now here, where pressure is increasing and volume is decreasing. So on the TS diagram, we can see that this will be our initial state point, and we are going in the reverse direction. So this will be the final state point after the end of compression. So here in this case, we see that there is a drop in the entropy. Now why the entropy is dropping? Because there is a heat rejection during the compression. So whatever work we are providing, the heat is rejected out of the system. In the initial case, in the initial isothermal expansion, we are providing the heat energy, and work energy is the output energy for us. But in case of the isothermal compression, the work energy is the input energy to run this particular process, and heat energy is the output energy from the process. So this is the representation of isothermal process on PV and TS diagram, that is isothermal expansion and isothermal compression. So moving further, for the analysis of this isothermal process, we are having the first parameter, that is the PVT relation. So when the equation for this process is given by the Boyle's law. We know that temperature is constant, then volume is inversely proportional to the pressure. So governing equation for this process is PV is equal to constant, that we already seen during the Boyle's law. So we can apply this particular governing equation to the state point 1 and 2. So we'll get the equation as P1 V1 is equal to P2 V2, that is equal to constant. Therefore, we'll get the pressure ratio and the volume ratio. So P1 V1 is equal to V2 upon V1. So this is the equations we can use to solve the problems. Then second point is the work transfer or the work done during the process. We know that the work transfer is given by W is equal to integration of pressure into change in volume, PdV. Now as pressure is changing, volume is also changing at the constant temperature. So we can replace the pressure by some term. So we are knowing that PV is equal to constant. So P is equal to C upon V, that is constant upon volume. So we are replacing the P here in the equation. W is equal to integration of C upon V with respect to dV. So C is the constant term. So taking the C term outside the integration sign, we are having integration of 1 upon V with respect to dV. Therefore, what is the solution for this integration? That is 1 upon V with respect to dV integration we are having log to the base E of V. Now here we are putting the limits because volume is changing. Volume is changing from V1 to V2. Therefore, we will get equation as C into log to the base E of V2 minus log to the base E of V1 by putting the limits. So log to the base E of V2 minus log to the base E of V1. So that is again simplified in the next step, and we are getting as W is equal to C into log to the base E of V2 upon V1. So this is the equation we are getting. Now we can replace C by the constant terms, that is W is equal to P1 V1 into log to the base E of V2 upon V1. Now this equation we can use it in the for solving the problems. That equation is the work transfer equation, in which we have considered here the volume ratio. Now we can simplify this equation. We can replace this volume ratio by the pressure ratio. So we can write in terms of pressure ratio, that is equal to P1 V1 into log to the base E of P1 upon P2. Now we can again replace this P1 V1 by general gas equation, that is equal to MRT1 log to the base E of V2 upon V1, or MRT log to the base of P1 upon P2. So we can use this particular equations according to the need of the problem to find out the work transfer during the process. Now the next parameter is the change in internal energy. So for all the gas processes we can use the similar formula to find out the change in internal energy, that is delta U is equal to mCV T2 minus T1. Now since T2 is equal to T1, therefore we will get T2 minus T1 as equal to 0. Therefore change in the internal energy will be equal to 0 as temperature is remaining constant. Now the next parameter is the heat transfer. Now from the first law of thermodynamics, dq is equal to dW plus du. So dq is equal to dW as du is equal to 0. So heat transfer is equal to work transfer plus change in the internal energy. Here the change in internal energy is 0. Therefore whatever the heat transfer is there, that is equal to the work transfer. So all the heat provided is converted into total amount of work or whatever work is provided, that is totally converted into the heat energy. The next parameter is the change in the enthalpy. Now for all the gas processes, change in enthalpy formula is same, that is delta H is equal to mCp T2 minus T1. Again, the temperature change is 0, therefore delta H is equal to 0. So change in enthalpy for isothermal process is equal to 0. Change in entropy, we know that change in entropy ds is equal to dq by T. So this is the formula to calculate the change in entropy. So the total change in entropy is given by integration of this. So integration of ds is equal to integration of dq by T. So delta S stands for total change in entropy, that is equal to. Now here in this case we are having 1 by T is constant because temperature is remaining constant. So 1 by T we are taking out of the integration sign. So integration of 1 dq. So integration of 1 with respect to dq. So we can write integration of 1 with respect to dq is nothing but the total heat transfer. So total heat transfer, we can use the formula of total heat transfer. So we are using this formula, that is mRT, because we are having in the denominator we are having T here, 1 by T, therefore we are using this formula mRT into log to the base E V2 upon V1. So T gets cancelled in the equation, so we are getting the final equation to find out the change in entropy. So delta S is equal to mR into log to the base E of V2 upon V1. So we can write this equation in terms of the pressure ratio as delta S is equal to mR log to the base E of P1 upon P2. So we can use either of this equation to find out the change in entropy during the constant temperature process. So we will solve the simple numerical on this particular process. So I will read the numerical. 1 kg of gas is expanded isothermally from initial condition of 0.1 meter cube volume and 735 kilopascal pressure to the final pressure of 118 kilopascal. Full stop. Find the final volume, then work transfer or work done, then delta U, then delta H and delta S. So delta U stands for change in internal energy, delta H stands for change in enthalpy, and delta S stands for change in entropy for the isothermal process. Now for this problem it is given, take capital R is equal to 0.264 kilojoule per kg degree Kelvin. So in the solution we are always writing the given data. In the given data we are first writing which type of process is there. So this is a constant temperature process. Now in the given data, first parameter is the mass of the gas. So mass is equal to 1 kg. Initial volume of the gas, that is V1, that is equal to 0.1 meter cube. Final volume we have to find out, that is V2 we have to find out. Then initial temperature T1 we don't know, that is not given in the problem. Then final temperature T2 is also not given in the problem. Then initial pressure P1 is equal to 735 kilopascal and final pressure is given, that is 118 kilopascal. So both the pressures are given. Then R value is given. Now we have to find out what is the final volume of the gas after the expansion process. Then what is the work done during the expansion process. Then delta U, delta H and delta S we have to find out. So we'll start to solve this problem after writing the given data. So we are first representing this process on the PV and TS diagram. So this is the expansion process. So we are drawing this particular curve along the constant temperature line. So So from state point 1 to state point 2, pressure is decreasing and volume is increasing along the constant temperature line. Similarly, on the temperature entropy diagram, we are drawing this particular horizontal lines from state point 1 to state point 2, where temperature T1 is equal to T2 and entropy is increasing from S1 to S2. So we can locate at different points, that is at state point 1 on the y-axis on PV diagram, we can write P1 value, then P2 value we can write, V1 value, V2 value, all the given values which we are knowing of pressure, volume and temperature, we have to write down on PV and TS diagram so that we can find out, we can locate which values are unknown values. So we can calculate those values from the PVT terms, that is pressure volume terms. So we'll note down those values here on PV and TS diagram. Then first parameter that we want to find out, that is the final volume V2. Now how to calculate this final volume? So we are knowing the pressure ratio and volume ratio. So P1 upon P2, that is equal to V2 upon V1. So putting the values, corresponding values of pressure and volume here, so we can calculate the final volume V2, that is equal to 0.62 meter cube. Now second parameter is the work done. So work done formula we are knowing, that is equal to P1 V1 into log to the base E of V2 upon V1. So putting the values here, we are writing work done, W is equal to 134.10 kilojoule. Third parameter, change in the internal energy, that is delta U. So we are knowing the formula for delta U, that is equal to mCV T2 minus T1. Since T2 is equal to T1, so delta U is equal to 0 for the isothermal process because temperature change is 0. Now change in enthalpy formula we are knowing mCp T2 minus T1, as temperature here also that is change in temperature is 0, therefore change in enthalpy is also 0. So when we are writing, we are knowing that these terms are 0, but when we are solving the problems, you have to mention that particular parameter, that is change in enthalpy, change in internal energy. In step by step we have to solve the problem, we have to write down this, because every step carries 1 or 2 marks. So you don't have to skip, you don't have to just simply write that delta U is equal to 0 or delta H is equal to 0, but why it is 0, that you have to mention. Then last parameter, that is the fifth parameter, that is change in entropy. So we know that delta S is equal to mR log to the base E V2 upon V1. So putting the values here, so we are getting delta S is equal to 0.481 kilojoule per degree Kelvin. So this is the total change in entropy, because we are considering the total mass here. So this is the solution of this particular problem. So we have found out all the parameters which are asked in the problem. So similarly, you have to solve the different more problems on isothermal expansion and isothermal compression. In isothermal compression, the reversal of this particular process will be there. All the formulas will be same, only some sign changes will be there in the solution. Therefore, we can easily solve this particular problems from this textbook. So for practice, you have to solve more problems on isothermal process, on all the processes you have to solve more and more problems from the textbook. Okay. In the next lecture, we will see the next process, that is the constant entropy process. So till then, thank you.